All right, let's take a moment and look at our list of assignments on the syllabus and see where we're going for the next couple weeks. You're off the hook for activities until next Thursday is the next one that's due. That's for parallax when we start talking about the distance to the nearest stars. But in the meantime, we want to talk about our solar system, and in particular, we want to talk about Earth-like planets and what NASA is doing to explore planets in our solar system, as well as explore different moons of the outer planets and things like that. So I've got my plan today here is to do a little tour of the solar system and talk about Mars in particular, because that's where most of the spacecraft and data are going these days, and then take a little bit of time to talk about the processes that sculpt planetary surfaces as far as Earth-like rocky planets are concerned. And then on Thursday we'll talk about gas giants and their moons, and move into that sort of stuff later on next week before we start talking about the stars. So that's the plan. I've got my chat window up here on the side. If you've got a mic, you can speak up if you have a question. I'm happy to stop and answer any questions you might have before we get going. All right, so what I've got in front of you right now is a program called Celestia. Now I'm sharing the screen on my computer, so you should be able to see this, although it might be a little choppy. So I am recording this if you want to go and watch it later. But this program called Celestia is a free program that you can download that is a 3D model of our solar system and, frankly, the galaxy and every known object that we have a distance to. So you can travel around and visit a bunch of places. It's just a little 3D modeling world to do that. And I'm going to use it to just do a brief introduction of the Earth-like planets before we start talking about Mars in particular. We might as well start with Earth, since we're most familiar with the planet Earth. This is a computer rendering with some satellite imagery put on board so you can see what the surface of the Earth looks like from space. One of the things that strikes us about the planet Earth right off is that it is the only planet in the entire solar system that has a liquid water ocean at the surface. The other thing you notice that there are clouds, and we have ice caps. I think you can see one of the ice caps down here. That's the Antarctic ice cap. So all three phases of water exist at the surface of Earth simultaneously. And this is really what makes Earth unique in the solar system, although it isn't the only place that has this environment where a particular fluid can exist in both the gas and the fluid and the frozen states. But we'll talk about that when we talk about the moons of the outer planets. So that's what we think makes Earth unique. The other thing about Earth that is unique, at least as far as we know, in our solar system is that it has life. Now, you can look at the planet Earth from space and tell that it has life. The trees, the green grass, the spectral properties of the continents tell us that there is life on this planet. The composition of the atmosphere tells us that there's life on this planet. And there is no other planet in our solar system that has the abundant amount of evidence that life just exists there in a huge amount. There are environments on Mars where you could have life. There are environments in the outer solar system where you could have life, but we've seen no evidence of it. Although that doesn't mean it's not there. It just might mean we haven't found it yet. Okay, so that's the planet Earth. One thing I want to point out before we keep going, though, is that one thing you'll notice about all the planets is that they're all unique. They all have their special environments and interesting facts about them. We think the Earth is the most unique because we live here, but perhaps if we happen to find some bacteria in the clouds of Venus, they might think that Venus is more unique than the Earth. So let's take a little tour of the inner solar system. I'm going to go to Mercury, for starters, the closest planet to our solar system, or to our sun. And here's the planet Mercury, and I'll zoom in a little bit on this. And if you look at the planet Mercury, it looks an awful lot like the surface of the moon, right? It has lots of craters on it. There's no there's nothing we would think of as a continent or an ocean or anything like that. We just see these craters and these cracks. One of the key features of Mercury is that it's incredibly dense. In fact, it's almost it's one of the densest planets in the solar system, and it also has a very large iron core and not much of a mantle. So one of the things we think with Mercury is that it got its mantle perhaps blasted off in a giant impact, and what's left is really more like the core of an iron-rich and nickel-rich planet. again, that's supported by our idea of these early heavy bombardment where we had planet formation and lots of planetary impacts. But the reality is we really don't know that much about the surface of Mercury because we've never set a probe down on there, and we've only visited it once with an orbiter. I guess twice now. There's a mission that's currently exploring Mercury. But there are places like here, this is just where we have no data. It's just blank because we've never seen that before. So Mercury is a very understudied planet. It's hard to get to. It's close to the sun. It has an orbital period of about 88 days, which means that it is pretty close to the sun and gets very warm on the daylit side. So it's a challenging environment to operate in. Okay, let's go to Venus now. Now Venus isn't all that much closer to the sun than the Earth is. The interesting thing about Venus is that even though it started out very similar to the Earth, it's a much different place. Now if we look at the surface of Venus, we see that it's pretty much cloud covered. It has a thick CO2 atmosphere, so thick in fact that the surface of Venus has an atmospheric pressure that's about 1,000 times what you have, sorry, 100 times. It has a surface pressure about 100 times what you'd experience on the Earth. These are high-level clouds that make it so we can't really see the surface. That thick CO2 atmosphere also makes it have a surface temperature that's about 500 degrees centigrade, about twice as hot as a pizza oven. So this is a pretty impressive place, at least in terms of pressure and temperature. The interesting thing is that it probably started out very similar to the Earth, same size, same composition, but just the fact that it was a little bit closer to the sun made it so that it couldn't have any water in its atmosphere, there couldn't be any plate tectonics to lock up the carbon dioxide into the ground, and it all got left in the atmosphere and caused this massive runaway greenhouse effect. This is the planet Mars, right? So Mars is further away from the sun than the Earth is, about 50% further away from the sun. It's Earth-like in a lot of ways. It has polar caps. You can see the polar cap here on the it looks like the North Pole of Mars. It has an atmosphere, thin CO2 atmosphere. The temperatures on the surface of Mars are extreme, but not outside the realm of human experience. In fact, there was a time this last winter where the temperatures in Michigan were lower than the temperatures on the surface of Mars at some places. So it's not outside the realm of human experience. And we're going to go into detail here in a second on Mars, because Mars is the one place in the solar system that I can imagine human beings visiting, other than the Earth and the Moon, within our lifetime. You can walk around on the surface with a pressure suit on. The temperatures are not outside the realm of human experience on the Earth. You would just need to worry about making sure you had oxygen to breathe and had a pressure suit on, because the pressure at the surface is about 1,000 times lower than it is at the surface of the Earth. So let's take a minute to talk about Mars, because right now Mars has a couple of rovers on it that you can explore for yourself. So if I go to the Mars Rovers website and click on Mars exploration, or the Mars Rovers from NASA, you'll see that we have a number of missions up there right now. The first two are Spirit and Opportunity. Spirit has or Opportunity has given up the ghost, or Spirit has given up the ghost, but Opportunity is still going around. So you can click on this and see what's been going on. Mars Opportunity is still finding things. It's been on the surface of Mars for 10 years, which is pretty amazing. The other one that has just been sent up there a little while ago is called the Curiosity Rover. And here you can see a little picture of the Curiosity rover, and this one is active as well, and it's roving around on the surface, taking pictures of rocks and potential lake beds and ancient river streams and things like that. So we're going to talk about those guys today. But in the meantime, if when you're just interested in looking around stuff on the web, you can check out these websites for the Mars rovers. Again, these are active on the surface of Mars as we speak. Okay, so let's talk about Curiosity, the most recent one, because it is the most advanced robotic spacecraft we've ever sent to the surface of another planet. It was named Curiosity as part of a campaign to find names for these things before they before they were launched to Mars, and it's surveying the planet looking for signs of water, or at least signs that water once existed on the surface. And the whole point of this is we figure if we can find environments where water existed at the surface, then we can find environments that if they don't have life today, they might have had life in the past. So a little history on observing the planet Mars. Mars has been known since antiquity. It's one of the 5 planets that that you can see unaided without a telescope in the night sky, and it's been known for ever since Kepler's laws that it's one of the closest planets to the planet Earth. It's also been known, at least for the last 100 years or so, that the surface temperatures were at least reasonable, possibly reasonable for life at the surface. And so it's been kind of a place that sparked the imagination as far as life in the solar system. Lowell Observatory, this is a picture of Percival Lowell, who was an avid Mars observer, and he built a telescope down in Arizona simply to get a better look at this planet. And at the time, it was the clearest, darkest sight, the best telescope for planetary observing that had ever been built, and it was built specifically to look at the surface of Mars. And you have to understand, at this point in time, we had no evidence one way or the other about what it was like on the surface of Mars, and yet, considering we had abundant life on this planet, there was no reason for us to believe that there couldn't be abundant life on the surface of Mars. So he probably started with a perception that there might be life on the surface of Mars, and so he wanted to go check this out. He built this fantastic telescope, and he started making observations. Now I want you to keep in mind that observations at this time consisted of a person looking through a telescope and then drawing a picture of what they saw. There were no photographic plates to speak of. They were just being invented at this time, and the photographic plates tended to wash out detail because you had to expose the plate for such a long period of time. So some of the best observations of planets were done exactly like you see here. Somebody sitting in a chair, looking through a telescope and making detailed drawings. This is a picture of what Percival Lowell thought he saw on the surface of Mars, and he made very, very meticulous drawings of what he called canals on the surface of Mars. And they were these linear striations that he saw on the surface, and nobody else saw these things. And part of that, he said, was because they didn't have a good enough telescope and a dark enough sight. And so he published these things in the popular press. He would give talks, and he wrote books about these canals on Mars that were feeding a civilization that lived on the surface of Mars. If you look at a comparison between his drawings and the pictures we have today from Hubble Space Telescope, you can see that he got some things right. I mean, if you look at this thing that he called Syrtis Major, this right here, this little feature, that feature is on the surface of Mars right there, and he saw something that he called the Solis Locus right here, that feature, that's the Hellas Basin, that is on the surface of Mars. He saw ice caps, which are on the surface of Mars. So he was seeing some things that were really there, but these linear markings, these canals, show no evidence of being on the surface of Mars. You can't see those in the Hubble Space Telescope images. So again, part of this was just because he was using an instrument that was really at the limit of its capabilities of finding and observing stuff on the surface of Mars. And so as he made his drawings, his brain filled in the details that he thought he saw. This happens a lot in science when we have to be careful about this in science, because if you're ever using an instrument that is at the limit of its ability to detect things, you have to be really cautious about how you interpret the results. Now this was so, he did such a good job of popularizing this, and you'll remember that it wasn't until 1969 that we sent the first probe to orbit Mars, to fly by Mars and see what it looked like. And even with our best telescopes, it was still just a fuzzy blob. So in the popular culture, there was a civilization on Mars, and even up into the point of 1938, when The War of the Worlds was done as a radio play. This was an H.G. Wells classic that was written at the turn of the century, but it was done as a radio play as late as 1938, and the people who heard the radio play in Grover's Mill, New Jersey, actually thought we were being invaded by Martians. This was not an unreasonable idea. I mean, for as far as the data goes, there could have been a civilization on Mars. It could have been attacking us, and they had to apologize for scaring all the people about the the War of the Worlds. We haven't been invaded by Martians, and there are no Martians living on the surface of Mars. But it's interesting to see how much that got ingrained in the popular culture at the time, based on a few people's observations and popularization. Okay, so this is what the surface of Mars looks like with our most modern instruments. These are taken from an orbiter orbiting the planet Mars, and you can see that there really isn't any of the stuff that Percival Lowell thought he saw. One thing we do see is an environment that has some amazing geological features. This is called the Valles Marineris, right here. This is called the Valles Marineris, and that Valles Marineris is so big that you could put California over here and Florida over here. It is literally one of the largest canyons in the solar system. It's so large that if you were to sit on this edge and look over, you wouldn't be able to see the other edge because it would be beyond the curvature of the Earth. Now, something else to keep in mind about this is that the Grand Canyon would look like this, that little squiggle. So this thing is enormous. This is an enormous canyon on the surface of Mars. Okay. The other thing you'll notice is the volcanic trio over here. These are the Tharsis volcanoes, very large volcanoes located on the surface of Mars. So there's clearly been some active geology in the past that has done some amazing things to the surface. Mars also has an atmosphere. The atmosphere is predominantly carbon dioxide, and it's very thin. If you wanted to experience a Martian atmosphere on Earth, you'd have to go up to about 100,000 feet. So if we have 1,000 millibars of atmosphere here at the surface, Mars has 6 millibars, so it's nearly 1,000 times less dense, the atmosphere at the surface of Mars. There's enough atmosphere. Oh, go ahead. There's enough atmosphere on the surface of Mars to allow for things like the deposition of carbon dioxide ice and also water ice. There is enough CO2 on the surface. If we could grow plants up there, it would be easy to do, but it's a very thin atmosphere. Mars also has polar caps. You can see the northern polar cap here, which shows predominantly water ice, although in the wintertime it gets covered with carbon dioxide ice on the surface. Here's a picture from this 1970s Viking Rover that shows water ice depositing in the early morning. So you can see here you've got some water ice forming right here on the surface that formed in the early morning and then evaporated later on in the day. So we have examples of water ice on the surface and CO2 ice on the surface, but we don't have an example of liquid water at the surface, at least not the way we see it on Earth. So we've got two of the phases of water, gas and solid, but we don't see the liquid phase at the surface. Now this is the largest volcano in the solar system. This is called Olympus Mons, and Olympus Mons is so large that you can draw the state of Utah right here. So the state of Utah is basically the same size as Olympus Mons. This volcano is so big that if you were on a hike up to the summit, you probably wouldn't even notice you were on a hike going uphill. It would be a very gradual slope up to the top. However, when you get to the top, you are 3 times higher than Mount Everest. This is an amazing volcano, and it shows you that the processes that shaped Mars were a lot different than the Earth. On the Earth, we have lots of little volcanoes all over the place. On Mars, we have big volcanoes in just a few places. So that just indicates that we don't have plate tectonics on the surface of Mars the way we do on the surface of the Earth. But this is an amazing volcano that there's really nothing like it elsewhere in the solar system. Okay, again, this is showing the polar caps. This one is showing the polar cap during the winter time, and you can see the extent of the ice has dropped down. But that's not why I'm showing you this. Why I'm showing you this is because of this guy right here, this huge dust storm, right? And in fact, it even stretches all the way up over here, and you can see there's dust all the way up here. So this is a dust storm that is spanning maybe a third of the planetary surface. So one of the key things about Mars that's different from the Earth is these enormous dust storms. Since there's no liquid water on the surface to absorb the dust, these things can get going and basically become planet-wide dust storms. Here's a comparison between Mars and Earth, showing the dust storm here on Mars. Again, this is the polar cap right here. This is the dust storm coming out from the polar cap, like that. Same thing on the Earth, right? This is the Sahara, and we have the dust storm coming out like that from the Sahara. Similar scales, right? But the difference is that Earth has this water right here. And that water can soak up the dust, and that dust is no longer available to be blown around. On Earth, that's not the case, right? On Earth, we have the water there. On Mars, that's not the case. We have the dust just blows and blows and blows. And I even remember one experience one summer when I was looking up at the surface of Mars, looking up at the planet Mars from here, from my house. I looked up and saw that it was its normal reddish color, and then a few months later I looked up and it looked yellowy. It didn't look like its normal reddish color. At that same time, I went and found Hubble Space Telescope images of the surface of Mars, and it had gone into what was called a planet-wide dust storm. This thing just covered the entire surface, and it was such a visible change I could see it with my naked eye from the surface of the Earth. So this is a feature on Mars that if we ever visit Mars to stay, we're going to have to deal with. Basically, we have these planet-wide dust storms where it's the equivalent of blowing cake flour all over the planet, and so whatever technology we have up there better be able to deal with that. And probably more impressive, or at least things that you might want to watch out for if you're walking around on the surface, are these things called, well, they're called dust devils, the same thing we have on the Earth, except these are dust devils that stretch up kilometers in height. They're not the little tiny dust devils that you have, and they leave these tracks on the surface that look like this. You can see these tracks, dust devil tracks that we can see from orbit. These things are so big. And we took a picture, and I don't know if you can see this on your monitors. You might have to come back and check this out. But this is a dust storm that was taken by one of our rovers, some pictures of it. And I'll play that again. You can see the dust storm right here, just coming across the surface. So these are things that it's just a fact of life on Mars. The dust is really the main problem. Here's a comparison of the heights of dust devils on Mars. Here's a terrestrial dust devil. This is what you'd see like in the deserts on Earth. This is a tornado on Earth. Here's a Mars dust devil. Here's the Himalayas. And then, just for comparison, this is Olympus Mons, which is 3 times higher than the Himalayas. So it's a pretty powerful event. And again, the winds would be something we would have to contend with. Now let's back up and look at the topography of Mars so we can kind of see what's happened at the surface. This planet is so interesting because it is the one place that human beings could live outside of the Earth. Now it's not as clement as the Earth, but there is water at the surface that we could mine and use. There are organic compounds that we could mine or use. So this is a place that if we were looking to build a permanent settlement anywhere else in the solar system, Mars would probably be it. And if we look at Mars, we see that it's had some pretty interesting geological history. The first thing you notice again are these canyons like Valles Marineris, the Tharsis volcanoes, and then we have Olympus Mons over here. So we see there's lots of volcanism, but what's more interesting is what the volcanism has released. If you look closely at this picture, you'll see that when Valles Marineris was formed, or at least after it was formed, there was something that something that flowed out of these areas pretty catastrophically. You can even see little channels going out like that. So this suggests the only fluid that we think could do this is anywhere near liquid near the surface of the conditions on Mars would be water. And the problem is we don't see any evidence of it today. So something had to happen to the water. It had to be escape off the surface. It had to go into the subsurface aquifer or something. And that's why NASA is so keen on finding this out, because this looks like there was a ton of water at one point in time. If you do the analysis on how much you can lose to space, you can't lose nearly enough water to make these features. And so the water has to be someplace on the surface, most likely in the subsurface. But it gives you an idea of why we're so interested in the planet Mars, because it has conditions, at least early on, that could have been very Earth-like. And that's why we're sending the rovers there to try and figure stuff out. You see features like this on the surface of Mars, and the thing that's so interesting about this one is you've got this channel. By the way, for comparison, you could probably put Weber State's campus right here. Okay, so here's Weber State. We see this channel that is carved, right? And that can happen by a lot of things. It can happen by lava, it can happen by glaciers, but what's more interesting is that there's this channel right in the middle here which looks like it was carved more recently. And so the only thing we really know that does that is long flowing liquid water. So again, more evidence of liquid water near the surface of Mars. If not today, then in the past, and this could have been 3 billion years ago, but it shows that there must have been a much different environment back then than there is today. A couple of other pieces of evidence that makes this so interesting. If we look at the craters, you can see this is a crater rim right here. So this is a big crater that goes around bigger than this image. I want to zoom in on this region right here. And if we zoom in on that, you'll see that we found regions in these craters that show river deltas. This is a big, water came flowing out here. Why do we think it's water? Because there's evidence of oxbow lakes, right? You can see these little flowing patterns here. You can see, places where streams crisscrossed, and if you zoom in on those areas, you can see places where the streams crisscrossed and changed patterns right here and right here. Again, that tells you that not only did something flow in there, but it had to flow repeatedly over long periods of time. And so this is an environment that would have been very conducive to the evolution of life, and so that's why we're interested in this kind of stuff. Places on the surface recently where we think we might be seeing evidence of this subsurface water seeping out are these gullies. And this is something, again, for perspective, you probably put Weber State campus right here, and we see a cap of stone, and then underneath that, these little seepages that run down along the surface. So again, it's hard to come up with any other explanation for this except for some kind of fluid flowing down, and the only fluid that would be a good candidate would be water. And you can see these things all coming down like this. The reason we think they're recent is because you've got a dune field down here. You've got dunes down here that are going like this, and wind on Mars is happening all the time, so those are forming continuously, and this debris is on top of it. And we call that the principle of superposition, that the thing on the top had to happen more recently than the thing on the bottom. So if you're forming dunes all the time, and then you have something up here that covers the dunes, that means this stuff up here had to happen more recently, which means it's happening all the time too. So again, evidence that there's liquid water seeping out of the surface. We find these all over the surface of Mars. So Mars is an interesting place. Everywhere on Earth we go, we find water, we find life. That's why we're focusing on this process on the surface of Mars. Now we've sent some rovers. I'm going to talk briefly about Opportunity, and then we'll talk more about Curiosity, because that's the really interesting one. But we sent a rover to Mars called Opportunity, and it used this process of a bouncing beach ball to land. Effectively, it was encased in giant balloons, and it got thrown onto the surface and bounced like a beach ball. And then it unfurled itself and took some pictures. And this was the first picture that Opportunity took from the surface. And you can see that it's on this very large flat plane, but it also saw this wall of rock. And the cool thing about this wall of rock is that it was laid down in place in layers. And that was interesting because we had never had a rover see that before. And if you look at that more carefully, you can see that there's some layers like this. They kind of cross go around like this. But the reason that's interesting is because layers means that you had to have some process that laid things one on top of the other. One of the best processes for doing that is liquid water. So this was the first close-up evidence of this layered material. Now there's other things that can layer material. Wind can do it, glaciers can do it. So we have to study these things in detail, but it got us pretty excited that we land on the surface and open up our cameras, and here we are. So where have we landed so far? To give you an idea of the perspective that we have on this, we've landed a couple times near the equator. So we had Viking 1 and Viking 2. Those were in the 70s. We had Pathfinder, the first bouncy ball approach. That was a little microwave-sized rover that landed back in the 90s. We then landed Phoenix up near the poles to search for water ice, and then we landed Opportunity and Spirit at the early part of this century to be the first more or less autonomous rovers at the surface. And now the big rover that we're dealing with right now is Curiosity. To give you sort of the perspective of how these things went, Viking 1 and 2 were landers that just came down to the surface and landed on the surface. Phoenix was a lander. Pathfinder was a little microwave-sized robot that was more or less autonomous, could drive itself around. Opportunity and Spirit were about the size of a golf cart, and they drove themselves around much more autonomously than the Pathfinder did. We could say, go to that rock, 100 feet away, and then it would try to find its own way there. Now, if it got stuck, it would have to radio back, but it had an ability to kind of find its own way through the terrain. And now Curiosity is about the size of a small crossover SUV, and it's doing the same thing. So we've really kind of ramped up what's been going on for robotic exploration of the surface of Mars, and we've been sending one about every 2 years for a while now. Where did we decide to go for Curiosity was based on the idea that these craters show evidence of ancient lakes. And so this is something called Gale Crater. It has a big mountain in the middle of it, and we had seen on this mountain a little channel that came down and fanned out into an alluvial plain, and I've got a picture of that here. If we look a little bit closer, this is that channel I just identified that comes down on the surface, comes down and spreads out into this debris fan. And then this is the error ellipse of the landing site for Curiosity rover, with the most likely landing site here. So the idea is to land here where it's flat and reasonably safe, and then drive up this thing. Okay, so that's the goal of this mission, specifically to look for evidence of liquid water. Now I've got a hang on. Okay, so this next thing is a video I'm going to show you of the ascent, the descent and landing of this Curiosity rover. They had to do some very unique things to make this work out, and I think it's fun to watch, because when I first saw this video I thought there was no way this was going to work. So this is just a few-minute video to illustrate this landing process.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror, because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow constrained space. This is one of the biggest challenges that we're facing, and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the sky crane maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage is in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
Now, I don't know about you or how well that came through on the conference here, but that looks like something out of an Avengers movie. You've got parachute descent, rocket descent, sky crane descent. It's crazy. And when I first saw that, I thought, there's no way this is ever going to work. Because not only did this have to happen completely automatically, because we couldn't communicate with it, it had to happen without testing it all end to end to begin with, because there's no way to test the parachute in Earth's atmosphere because our atmosphere is too thick. There's no way to test the sky crane because the gravity's all wrong. So they had to test it all piecemeal and put it all together and just hope it worked. And it worked beautifully. It was amazing. Now you can go see the actual descent video on YouTube. Let's go full screen. Now this is an actual descent video. What we saw just recently was a 3D animation of what happened, but this is the cameras on board the spacecraft showing you exactly what happened. So if we play this, you can see there's the heat shield falling down to the surface. You can see the dunes that we're going to land near down at the surface. In a second here, you'll see the, right now we're coming down on the parachute, which is why it sort of seems like we're just bobbing along here. And in just a minute, we're going to cut the parachute and come down on the rockets. And then we just cut the parachute, we're coming down on the rockets, and then we fire the rockets near the surface. We get a little bit of dust up, just a little bit, and then we lower on the sky crane. Here comes sky crane down, boom, touchdown on the surface. Now here you can see we saw an orbiter watch the heat shield smash into the surface, and we saw later on, if you look at some of the imagery that we took from orbit, you can see the sky crane where it crashed. Here's the sky crane. Right here, the sky crane smashed there. Here's where we landed, Curiosity. Here's the back shell and the parachute that we cut off, and here's the heat shield over here. So we got to see this happen in real time, and we know exactly where this rover is. Now, when it first started to plan its route, it landed right around here. Sorry, it landed right around here. You can see where you've got all the, the recent material has been blown away by some of the retro rockets, and then it's going to make its way over here to this outcrop, and that's the thing we're going to look at first. So this is the first picture from the surface. It was I only show it because it was the first indication that anybody had this was successful, and it came 14 minutes after the probe landed on the surface. So you can imagine the engineers sitting there. They knew that it had either landed or crashed, but they didn't know for 14 minutes. And then when this came, you can see the lens cap is clear. It's got a little bit of dust on it, but it's the first image that came back. Now the images going forward, though, once we got the lens cap off, are pretty spectacular. So here's a picture of the surface of Mars where Curiosity landed, and frankly it looks an awful lot like southern Utah. I can find areas in southern Utah that look just like this. And here I've got something where this is going to move across the screen for a large panoramic shot, and you can see Mount Sharp in the background, and you can see the terrain around the rover. So it's a pretty nice, safe place to land, and it's got a pretty good view, and we're going to drive over to those mountains and see what's going on. So let's take a look at that again. There's Mount Sharp, and you can see where that canal is coming down a little bit as you pass by, and then you can see the mountain range, the crater rim in the background here. So this is where Curiosity gets to play around for the next year or so, and it's already been, let's see, it landed in August of 2012, so it's already been almost a year and a half on the surface. Here, I don't know if you can make this out on your screen, but this is that channel that comes down from the top of the mountain. So that's where we're headed, and we're not there yet, even after all this time, because we're exploring things on the surface as we go. Now, I want to show you just one example of why this was an important site to go to, and probably one of the best pieces of evidence I've ever seen for liquid water at the surface. Shortly after Curiosity landed, it found this outcrop, and again, layered material is good. Layered tells us that stuff has been deposited over time, and so we can study the sequence of events. If I look at a close-up of this layered material, I see gravel. Now, gravel is pretty amazing stuff, because if you look around where we live in northern Utah, we have a lot of gravel pits. Why do we have a lot of gravel pits? Because gravel is formed at the place in the river where the speed of the river slows down, that the gravel can drop out of it. And this gravel, really the only way to make gravel is in riverbeds over long periods of time. And even if you compare the gravel to what we see on the Earth, so here's gravel on Mars, and here's gravel on Earth. And you can see that the size, shape, distribution, color is very similar to the gravel we see on Earth. So you can go up Mount Ogden Canyon and look at just right as you come into the canyon and past the aqueduct and the waterfall. If you look to your right, you'll see this big wall of gravel. You can see all the little gravel pieces. That's what we're finding on Mars now. We're finding evidence of gravel at the surface. So this is exciting. We go all the way to Mars to look for a gravel pit, but gravel pits tell us that you had liquid water running for long periods of time. Now, just looking at the time here, I've only got a few minutes left, but I want to just give you an idea of where we are on Mars exploration, so you know where we're going. Now, these dates are a little bit off because we had that pesky little recession, but we're pretty much on track as far as when the order of operations. So we have on the surface of Mars now, we have one of the Mars rovers is still going. Opportunity is still running. Spirit is dead. We have the Mars Reconnaissance Orbiter. That's flying and on track. Phoenix has landed. That was a successful mission. Mars Science Laboratory. This is Curiosity rover. That's on the surface and doing what it needs to do. And this Mars Telesat is something that we're looking to launch in the next orbiter to get information from the orbit of Mars. And then, depending on what we find, we have to decide what we're going to send next. We have found evidence of liquid water in the past, and so the next step is to send something that can analyze that evidence to see if we can detect if life had ever been there or not. And the next step is something called the Astrobiology Science Laboratory, which hopefully we'll be launching in the next few years. You can kind of see what the future is holding for this. We have the European Space Agency is working on a Mars rover. We have our Mars Science Orbiter, which we're planning on sending. And then, depending on what we find, these are the types of options of what we might send. People are pretty much leaning towards the Astrobiology Field Laboratory, because this will be something that'll be curiosity, souped up curiosity to basically do in situ analysis of rocks on the surface of Mars. And the ultimate goal of this is to find something worthy of sample return back to Earth so we can analyze it in our laboratories to see if it has any evidence of life.